Thank you. So many. This another port. Okay. So good morning, and everyone. My name is Sheng Yu Peng, and I'm from Taiwan. And I just switched to a new school last year. So right now I'm in the National Ming Tung University in Hsinchu. And I really appreciate this opportunity to come over to share my research experience with all of you. And thanks Professor Chetan for the wonderful arrangement. And also I bring two of my students with me so that they can learn a lot. So I really appreciate these opportunities. And things like in the last year, I already gave the talk, and then also during last year, I'm actually during the transition. I'm afraid like the material will not be updated too much, but I try to organize a little bit, so bear with me. And so this is a school, the new school actually I'm at. So actually this school actually is merged in 4 years ago. So previously there's a Ming University in Taipei City, and there's a Chiao University in Hsinchu. And then in 2021, these two schools merged together so that we have hospital and also the medical school, and then also the lots of engineering college. So right now in this school, actually, we have 20 colleges and 1 hospital in Yilan. And then we have actually 10 national labs. So actually this is a major research university in Taiwan. And more than 1,000 faculty members and about like 20,000 students. And right now we have lots of sister schools with dual degree program. So we are actually look forward to international collaboration. And so I also look for all the international collaboration opportunities through this workshop. So the lab actually started like maybe 4 months ago. So right now I only have 2 graduate students and 3 undergraduate students. So, so the research interest, as I had before, like I'm an analog circuit designer, so I try to design circuit for AIoT, like the artificial intelligence of things, and then hopefully like I can solve from energy to cognitive computation. And then so I have some circuit about like energy harvesting, the thermoelectric converter, and then we have done some research about buck converter for power management, and then low dropout regulator. And then for the analog sensing front end, we have circuit from low noise amplifier, filter, ADC, buffer, and then input driver. And then recently we are doing the cognitive computation circuit. So we have 2 circuit. One is called RCCM, reconfigurable cognitive computation matrix. And the other one actually is ongoing. It is called analog GRU. And besides circuit, actually I also involved some integration project with other professors in other universities. So previously we have done some red experiments for seizure suppression. And then we are also collaborate with some hospitals by using the millimeter radar signal to reconstruct the ECG signal. And then we also try to use the low resolution thermal imager to do the gates distinguish. So this kind of the whole research interest I'm involved. And today's talk, I try to talk about the neuromorphic integrated circuit for cognitive sensing at the edge. And I think this is the neuromorphic workshop, but instead of the neuromorphic circuit, I'm more like using the neuromorphic engineering approach to design integrated circuit. I try to use this kind of philosophy to prove like neuromorphic engineering actually can help traditional analog circuit. So I think we know that this is the era of robotics and unmanned vehicle and edge AIs. So there are lots of sensors coming out every year, and then lots of devices will have more and more sensors integrated in the unmanned vehicle or robot. So this kind of mobile platform, actually, they demand real-time responses. So that means like low latency. And also because of the limited form factor, the battery is limited. So actually they have very strict constraints in energy and battery life. So when people are trying to develop this kind of mobile platform, intelligent platform, actually they still have the expectations, hoping these kind of devices actually can have a supercomputer kind of performance, but just using a coin battery. So what is the barriers or walls to prevent this happen, or what's the bottleneck right now? I'm thinking. I think this is kind of stem from the von Neumann architecture proposed in 1945. At that time, actually, I think von Neumann used the divide and conquer approach so that people can try to separate the processor and the memory in different fields. And then by doing so, the processor and the memory can be optimized individually as long as the connection, which is the bus, have enough bandwidth. So this is the assumption for this von Neumann architecture works for more than 50 years. And actually, because of the Moore's law, like the golden era from 1970s to 2010s, the semiconductor manufacturing followed the Moore's law pretty well. So that means like the number of the transistor in the processor and also the speed of the processor can increase, become more and more devices, and the processing speed become faster. And by the same time, the memory foundries also benefit from this Moore's law. So you have more and more large memories, and then the density become larger and larger, and then the price of the memory become cheaper. And also at the same time, the bus between the memory and processor actually is still high enough. So you can still use the Moore's law to increase the data transmission baud rate. So everything seems fine because this architecture flow actually is hidden by this roll speed improvement during the Moore's law. But by doing so, actually, we actually create some cultural walls. Or we can say this is the formation of the industry's silos, which means like by doing so, ASIC people like analog circuit designer or digital circuit designer, they try to focus on their expertise in their comfort zone only. So they choose to design circuit as fast as possible, and then with a very, very high switching speed. And for memory foundries, they focus on the bit density and also the retention time, right? So the designers optimize within the blocks and not crossing the boundary anymore. And then in the circuit side, there's analog and digital. So this kind of culture also exists between sensing and processing. So as long as like there's an ADC, they kind of build the ADC wall. So for analog circuit designer, usually they just try to convert everything into digital bit using ADC. And then the digital processing people, they just require as much data as possible so that they can perform signal processing. But the problem is like, by doing so, when people are asking the criterion of ADC, they always ask for Nyquist ray sampling because they don't want to miss anything, which is might be important. But whether it is important or not, the analog circuit designer would not know. Right? And then for digital circuit designer, they don't want to miss all the information, so otherwise they might have ineffective signal processing. So lots of data movement happens due to this power hungry, and then I call it as a ADC wall. But if you think about it, like all the analog signals has some sparsity, right? So when you try to use Nyquist ray to sample this kind of signal, you actually sample lots of silence or noise signal, which is of no importance. So is it a waste of energy and the power? And the other kind of design trap actually is designed by worst scenario or designed by worst case, right? So this is always the disciplinary, or this is kind of the guideline from professors in school to teach students to run all the PBT corners when they try to design the analog circuit. And then I also heard from the company, they say like there are about like 283 corners because you need to worry about temperature, process variation, and voltage variation. And because different kind of foundries, they have different components. So different components have their independent corners. So if you try to multiply all the number of processes or variations, then the number of the tests or verification you need to verify will add up quickly. And so people try to say like to have to be able to have a mass production, this design for worst scenario actually become the wall between sensing and computation. It's just like when people are doing computation, they worry they don't get enough signal or information from sensing side. So when the Moore's law is still good, then everything seems fine. But when Moore's law is slowing down and the Dehner scaling law is also dead, then that means like the power efficiency and also the power density is no longer keep constant when the process keeps shrinking down. And also the logic becomes faster than the memory. And then in this way, actually you have two walls. One is the power wall, and the other one is memory walls. And the CPU gradually spend lots of time just waiting for data. The bus is not fast enough. So people tried all the efforts to try to speed up. And then this kind of data movement actually become worse. So we know like the CPU to perform computation, the energy is quite low. And then if you want to move the data from DRAM, actually the energy will be 100 times more than the computation. So that means like most of like only 10% of the energy actually is used in computation, but 90% of the energy actually is waiting for data. So this is actually the table Professor Arindam just showed in like 2 days ago. So like the 14.16-bit multiplication need 1.1 picojoule, but if you try to access the 1 megabyte cache, actually it takes 100 picojoule. And then when people are trying to solve this problem, people try to use the 3D fabrication technology. They have the through wafer via, and then try to stack all the memories and then try to put the memory as close to the microprocessor as possible. And then you can see this is kind of the processor actually where the GPU we are using nowadays. But still, like you can see, no matter how close it is, the processor and the memory, they are still in two different entities, right? So there's still some like a physical connection between the memory and the processor. So because of this kind of data movement, energy is huge. So people are talking about nuclear for artificial intelligence. And then if artificial intelligence needs such a high energy, then what can we do about intelligent robots and AI at the edge, right? So I think this is the reason why we are resort to neuromorphic engineering, because the human brain, human intelligence only take 20 milliwatt of power, and then it can provide the solution. And so to me, the neuromorphic engineering principle actually is the fusion of sensing and computation with distributed memory, and also nonlinear operation, the reconfigurable hardware, asynchronous timing, and parallel and scalable architecture. So in my research in terms of analog circuit design, I try to use this kind of principle and then try to see if I can make this circuit performance better and also more power efficient. And right now the memory I have access is embedded analog flash and also the SRAM. So actually I'm working on the circuit with these two memories. And hopefully in the future I can get some like RAM or some emerging memory soon with other professor's lab. So breaking the walls, I think we need a paradigm shift. Right? We need to design from a paradigm of separate memory, computing, and the sensing, and then become the fusion of memory and computing and sensing, right? And then from digital-centric design, become like analog-centric design to avoid the digital data and also the digital memory resources. And then supposedly we should not stick to the worst-case design philosophy. We should try to shift to the adaptive design, which means like the analog circuit design should be adaptive to the input signal so they can adjust its configuration and then to save power. And also we should design the reconfigurability for intelligence. So this is kind of the way I'm thinking about like neuromorphic engineering as a solution for edge AI. So in the following, I will try to use this kind of approach to share my design experience of some key circuit blocks during the last 10 years when I was in NTUST, my previous school. So the memory I use first is the analog flash memory because I learned this from Georgia Tech from Dr. Hustler. And then this is an interesting device because it is just a capacitor with a transistor and the gate is floating. So if you have a charge on the floating gate, because it is isolated by good insulator, so the charge retention time will be long enough. And then if you use the charge reservation low, you can observe or you can derive the floating gate voltage actually can be written as the weighted sum of the input voltage and also a charge term. And if you can program the charge precisely, actually you can use this kind of flash memory, analog flash memory to do lots of interesting things. And on the left is the measurement result at the Hustler's lab when I was in a PhD student. Like my lab mate actually measured like 128 different floating gate transistors with different current level with 0.2% of accuracy. So I think this technology actually is mature and feasible. And then if you have this kind of analog precise programming capability, we can rethink of this simple two capacitor in series connection circuit. And then you can see the output voltage actually can have the red part of weighted sum operation and also the blue part of the Q. And Q actually is the charge stored on this floating node. So if you can adjust the charge of Q, actually can change the DC level of this circuit. And the interesting part is like this kind of operation or functionality, you don't consume any static power because there's no DC current flow. And then also capacitor is it's not a resistive device, it's not a passive device, so there's no internal noise. So you can actually perform operation without noise, without power, and then if you use this kind of technology in your circuit design, actually you can get some benefit. So I use this kind of design philosophy in the low noise amplifier. So if you have a capacitive feedback amplifier and the noise is dominated by the OTA itself, so in this OTA, if you use a complementary differential pair to load differential pair with each other, then actually the noise will be pretty low. And then if you want to have a differential output, 40 differential output, you need to have a common mode feedback. So as an analog circuit designer, we don't know like common feedback, you need to take the average of the output voltage, right? But previously, people would try to use a source follower or try to use a resistor with a parallel with a capacitor and then try to make summation. But if you are designing low power circuit, the resistor will be very large. Otherwise, your circuit will not be able to drive the common feedback resistors. But if you use a 14 gate in the bottom transistor and then you have two identical capacitors C1 and C2, then you can make this 14 gate voltage to be the average of the output, two output voltages, and for free because there's no DC power anymore, and then there's no introduced noise. and also it's very fast. And then for the feedback resistor, previously people used the dial-connected pseudo resistor with lots of nonlinearity. And we also know, like, if you want to have a good linear pseudo resistor, you need to modulate your gate voltage to be the mean of your source and drain voltage. So how do you get the average voltage of the drain and source? We can also use the 14-gate approach. You can use again, like 2 equal value of capacitance to couple the source and gate voltage equally into the gate. And then by doing so, this pseudo resistor will be very linear. Again, it will not introduce extra noise or power. And another good thing is, like, you can adjust the charge on this 14 gate. So by adjusting the pseudo resistor charge, actually you can tune the pseudo resistance value. And then if you change the charge on the common feedback 14-gate transistor, actually you can tune the output DC common level as much as you want. And then in this approach, we also try to use the 14-gate at the tail transistor so that you can try to program the charge, and then the OTA will give you different GM and then different bandwidth, and then you can use the same hardware and then to fit into different kind of biomedical signal sensing scenarios. So this is kind of the results. We can actually tune the pseudo resistor value to tune the high pass corner, and then we can tune the tail transistor, the OTA GM, to tune the low pass corner. And then we can program the same hardware to be like 100 hertz, 1K hertz, or 10K hertz. And then we can measure the noise and then power supply, the power, and then also the linearity. And this noise efficient factor, which is the figure of merit to evaluate whether this topology is efficient or not, actually is 1.88. And this is, I think this is the first circuit actually below 2. So this is the work we have done like 10 years ago. And then after the LNA will be the filter, and the filter will be designed with this nonlinearity and reconfigurability. So for filter, no matter what kind of filter profile you want to use, actually the topology will be the same. As an OTAC filter, you just have to change the current, and then your GM will be changed, and then the quality factor or center frequency or the gain of the filter can also be modulated. So that means, like, as long as you can tap out the hardware chip, and then you can have the ability to program the charge individually, you can try to create as many kind of filter profile as possible. Another thing of this 4 OTA 2 capacitor type of filter is like the input impedance is infinity, so you can cascade them without worry about the loading effect. So by doing so, you can actually create or get a low pass output or band pass output. So it's a very diverse or type of filter topology. But the bad thing is just the linearity is not very good, because when you are in the subthreshold region for biomedical signal, the bandwidth might be about 100 hertz or K hertz. Then you use subthreshold current. Then this subthreshold current GM will not have a good linearity. So this is kind of the basic differential pair. This is the GM profile. So you can see if the GM deviates by more than within 1%, the input range is only like 14 millivolts, which means like when you change by 14 millivolts, then you can guarantee your GM value will be almost constant, like 99% of accuracy. But if you're in differential voltage outside 14 millivolts, then it's not good enough. But however, the filter actually is, the filter follow the low noise amplifier. So the input signal has been amplified. So the input signal can be as large as 100 millivolts. So how do you try to extend the input linear range as much as possible with a very low power consumption? Actually, is a very interesting research topic. So in the first beginning, we actually look into different kind of linearization technique. And then we try to evaluate. Actually, we propose a linearity efficient factor. And then we try to see like, oh, if you can use different kind of nonlinearity and then try to do nonlinearity cancellation, and you can actually get a very flat GM profile. And by doing so, actually you try to make use, instead of like ignore or eliminate the nonlinearity, you try to make use of the nonlinearities of different pairs. So on the bottom, you can see like actually in the right-hand side, you have 4 different differential pairs and separated by diffusers. So when you try to tune the diffuser's length, W/L, and also the differential pair's size, you can try to adjust the width and also the height of this small bump. And somehow you can try to manage to make them compensate for each other, and then the sum up of the GM will be flat.
Excuse me.
Yes.
Previous slide, you have a filter.
Yes.
You say it's nonlinear. How do you specify the frequency response?
How do I specify the frequency response? Linearity will be specified by, if it is a bandpass filter, we'll use a two-tone test to evaluate its third harmonic component, and then if it is a low pass.
Is it a frequency sweep?
Mm-hmm.
Is it a frequency sweep that you are trying to?
Yeah, it's a, you will use a spectrum analyzer, so there's a frequency sweep, and then input signal you can input 2 tones, and then because you have a third intermodulation tone just beside these 2 tones, as long as these 2 tones are close enough, the third modulation tone will still in the pass band. So then you can use this intermodulation tone to evaluate.
Can we quantify that also?
Yes.
How much is the nonlinearity effect?
Yes.
Is it 10%?
Actually, the interesting is like, one thing I didn't explicitly say is like, in this kind of topology, actually, the nonlinearity might cancel with each other. Because you have a GM and you have a diconnected GM, so they will have a nonlinear function and the inverse nonlinear function in the DC path. But you can hardly imagine whether everything will be exactly the same. And also, if you have a basic differential pair, when your input signal is large, then your linearity will not be good either. So instead of looking into the complete filter linearity, we try to say like, hey, if I can start from the GM, if I can linearize the GM, then even if with this kind of inverse function kind of compensation, I will still be better.
Is it possible to get a bandpass filter?
Yes. Yeah. So there's a low pass output and there's a band pass output. So you take the green net, it will be the low pass output, and if you take the black net, you'll get the band pass output. So there's a multiplexing you can select. Yep. So if you think about it, how do you, if this kind of linearized GM actually is a very, very interesting circuit design problem, because how do you convert a large voltage to a small current so that you can have a very low power consumption with very good linearity, right? So usually if you want to convert a large voltage to be a small current, you need to have a very large resistors. If you have a large resistors, then you will not be efficient in your IC fabrication because it might be, the area will be too large. And then, so previously we talked about a pseudo resistor. I think that's one of the approach, and this one, like if you can have a differential pair, linearized differential pair, and then somehow it can also be used in other applications. And then we try to analyze this topology and then also analyze the noise. So we can, from simulation, we can actually see like in this kind of OTA, we can actually get dynamic range improved by 14 times, almost 15 times. And the power penalty is only like 57%. And the input linear range actually can increase by 17 times. So actually it's a very good topology to achieve low noise, slightly higher noise, but slightly higher power, but very large linear range, and then good efficiency. So this is the measurement result. So we can take the GM differential pair and then measure the current and then try to sweep it and then try to do a derivative, and then we can get the GM profile. So you can see actually, because as long as your transistors are in the subspatial region, then they'll be very flat. But once some of the transistor in the upper threshold region, you can see some of the bump coming out. So they still have some range, but the feasible current level you have to specify. But as long as you are in the subthreshold region, that's fine. That means that as long as you are in the low power mode, then you are fine. So this is a chip, and then we actually make 6 different backquad, and then you can do the connection. And then so we try to implement 12-order Butterworth filter response, and then 6-order Chebyshev bandpass response, and also 6-order low-pass basal function response to see the constant delay response. So this is so another one, the other circuit to use the nonlinearity is the ADC. So if you think of ADC, like previously people try to convert the ADC in binary search manner. So they'll start from the largest cap and then switch and then try to check with the second largest one, and each of the cap are weighted binary. So if your signal is not large, is it possible to bypass those kind of big cap switching to save power? So this is the idea of the bypass ADC. So that means like if we can have a good way to detect the signal level in advance, then I can save lots of cap switching power and also the SAR logic switching power. So this is so we try to we propose a dynamic proximity comparator, which means like this comparator have 2 outputs to indicate the polarity and also the proximity. If the signal is within some specific range, this proximity comparator will tell you this is high or low. So if it is in the proximity, which means that the signal level is low, then we can perform the bypass operation, and you can skip like up to 4 different conversions. And then to do that, we actually try to use Toby's bump circuit. I think if you are familiar with the bump circuit, you know that it has a bump shape. And then you try to make the circuit topology symmetrical so that the bump shape will be symmetrical. And if you compare this bump shape of transfer characteristic with differential pair characteristic, you can actually see there are 2 intercept points, and then you can use that intercept point as a threshold voltage to trigger the second stage latch. So you can use one of the one of the 2 nodes to determine the proximity, and then the other 2 nodes to determine the polarity. So the dynamic switch, you only have to reset it once, and then you can have these 2 information. And then this is kind of the illustration. Like if your signal level is high, and if the signal level, the white one will be the one you will not be able to bypass. But if your signal is within the gray bar, actually those kind of conversion will be skipped. And then as long as your amplitude becomes smaller and smaller, the amount of power saving actually can be more and more. So it's actually a amplitude or signal dependent kind of conversion. Yeah, so you can see like this, the figure of merit or power, we actually input the ECG signal and also the sine wave signal. So if you use the sine wave signal, which means like the worst case in the Nyquist rate, right? Then you get like larger energy. But if you use the ECG signal, because most of the ECG signal might be in the zero amplitude, then you can bypass lots of switching, and then you actually can significantly improve the efficiency. And then buffer amplifier. Buffer amplifier is also interesting because if you think about buffer, or if you think about biomedical signals, they have some sparsity property, right? Which means like the rapid transition actually is very short. Most of the time, actually the signal is smooth. However, those kind of rapid transition region usually contain essential biomedical information. So when you try to design circuit, you want to catch this rapid rise and fall quickly to avoid missing the important information. So on the left, this is the ECG signal, and then we can see like if you do the first order derivative, it can kind of become the slope, the slew rate. Or the slope is the slew rate, and you can see like 94% of the time, actually the slew rate is within 0.1 times of the maximum slew. And then if you look into the neuron spikes, it's even worse, right? 96% of the time, this slew rate actually is 0.1 times the maximum slew rate. However, if you want to get a fast spike, usually people will use that as the worst scenario to design their power consumption. That means like you spend lots of power, but maybe like 94 or 95% of time you really don't need to use it. You just use the power in case the spike come out. So what can we do about it? So you can see like the slew rate actually is the delta voltage divided by delta T, and it's usually determined by internal current and some parasitic capacitance. So if you want to have a very high slew rate, then you need to have a high current, right? And then because the capacitor might be fixed and then the amount of voltage change is given by the signal. So how do you achieve high slew rate and a low current? Actually is a dilemma. So if you want to do that, supposedly if you use the conventional basic differential pair, then you will have a hypersine type of transfer function. When the signal is large, actually the current is constant, then you are kind of stuck at that region. That means like when the signal is large, then you need to tune up this flat level, saturation level. And that means like even so when your input signal is small, you still keep this high biasing current level. So instead of this kind of sigmoid type of transfer curve, we resort to the hypersine kind of push-pull KSAB transfer characteristics. So this is a circuit by Professor Ming. And then because he also used the 14-gate kind of approach, so the input actually can be rail to rail, and also you can use the charge to trim the offset. So we take this kind of circuit as the input stage. So if you have this kind of input stage circuit, that means like as long as there's a large difference at your input, the circuit will automatically generate huge amount of current to charge the capacitor so that you can have a high slew rate. But if this input voltage becomes small or it becomes equilibrium, then actually your current can get back to the low current level. Then you can achieve low quiescent current. And then we combine this KSAB input stage circuit with a cat feedback amplifier. So if you try to add another two capacitor, one is the input capacitor, one is the feedback capacitor, and then share the 14 gate, you'll find this circuit is very interesting because the feedback capacitor, like the CF1, actually can sense the output voltage, and then the C-in will sense the input voltage. And the summation will be merged at the 14 node. So this 14 node, actually because you have negative feedback and assume your amplifier has a high gain. So that means like if everything is in the equilibrium, nothing is changing, then your 14 node voltage will have a virtual short property. So these two node voltage will be very close to each other. So remember, like if you have a KSAB type of input stage, that means like hey, your circuit will be in the low power quiescent mode. However, if you have some perturbation at the input, this input signal change will capacitively couple to the 14 node. And in this 14 node, you will try to change this delta voltage in the 14 net. And then once this delta voltage becomes large, then the input stage simultaneously increase huge amount of current, almost exponentially. And then this current will try to drive the output load capacitance and try to make this output voltage to reflect the input change. So when the output voltage sense the current and then try to settle to the desired value, then this output voltage will feedback through this feedback capacitance and then try to modulate another 14 gate. So gradually these two 14 node voltage will also close to each other. And then once they are back to the equilibrium, then again you'll get into the low quiescent power mode. So this is a complete circuit. It's just like you have the Professor Ming's input stage, and then we have a 40 cascode topology, and then there's a class AB output stage, and then we have cascode biasing circuit. So if you use this kind of topology, actually you can see something interesting. If you have a step response, right? So when people try to evaluate the slew rate, they use the step response to see how fast your output voltage can change. And then if you look into the red color, this is the peak current. When you have a sudden change, then the circuit power supply current will change dramatically and then drop back when the output kind of settled. And this peak supply current actually is a function of your step size, which means like when your step is small, then this peak current will be small. If your peak step is large, then this circuit will automatically request a huge amount of supply current, try to catch up as soon as possible. So then, and then if you input the sinusoidal wave, not the step function, just the sine wave, and then you can have this, the red one is the frequency response, which means like your corner frequency is around like 10K hertz. So when your frequency is small, is low, much lower than the circuit bandwidth, 3 dB bandwidth, then you can see the power consumption will be low because the output always follow the input nicely, so you don't see too much variation at the pseudo-14 node. But when the input signal becomes faster and faster, this circuit will automatically increase its power consumption, try to catch up the input signal. So then you can see the power supply current increase, and then to the point he cannot follow the input signal, then you just drop. And then so that means like the power supply current is a function of input frequency. You just burn sufficient amount of power to catch the signal you want to catch. And then if you change the sine wave magnitude, the small magnitude, then the power will also become smaller. And then if you have a large amplitude, then your power will automatically increase. And because your power increase with large amplitude, so your circuit bandwidth also increase. So that means like when we are learning about bandwidth, we say it is the small signal parameter, right? Which means like the input signal should be very, very tiny, very small. And then if you have a large signal, actually you become the large signal behavior. So actually this circuit try to mix this kind of concept, like this small signal parameter bandwidth actually is a function of your large signal amplitude. So, and if you look into this kind of measurement result, that just means like this amplifier is intelligent, right? Because we don't need to tell or tune this tail current or the circuit. It can sense the input signal directly, and then you can sense the output voltage. And then if they are matched, then you kind of remain at a low power level. If there's any change, depending on how large it is, you automatically source sufficient of current, try to maintain good linearity. And so we use this kind of design concept in ADC driver. For ADC driver, actually consume much more power than ADC, even so like people design ADC, they usually don't include the power consumption of the ADC driver. The ADC driver actually need to make the output voltage to follow the input within very short period of time. And then when you are sampling, one is the slewing phase, the other one is RC scaling phase. And then when you are holding, supposedly the output is not changing and the input is changed, right? And then because assume your sampling capacitance, which is the cap array of the ADC, so when you are in the holding mode, you are actually just loading a very small capacitor. So that means your output can follow the input nicely. Supposedly your ADC driver doesn't need to consume too much power. But when your switch is closed, try to make this ADC input voltage to follow the driver input, then you need to have a very significant amount of current to charge the capacitor fast enough within almost like maybe much less than half of the sampling period, right? So how do you try to do that? If you look into the equation, we know like this amount of current is equal to the load capacitance times how much voltage, and this voltage can be the Nyquist voltage, will be the full-scale voltage, and then Ts actually will be the sampling period, the whole period of the sampling frequency. So people try to design some topology using like change the load capacitance or changing the sampling frequency or changing the delta V, and then they'll create a lot of circuit complexity. So in our approach, we just say like, hey, can we use this kind of class AB adaptive input stage, and then we can change this current automatically. So again, you can see this very similar like Professor Ming type of class AB input stage, and then we just simplify the output, and then we can drive the ADC driver. And then this is like, if we try to check with the class A type of ADC driver, we can actually save more than 50% of power consumption. And then we also use this kind of adaptation in the low dropout regulator, because in the low dropout regulator, you have error amplifier, right? So this error amplifier will only change when you have a load change or input change, right? So if input is stable, if output is stable, supposedly your error amplifier supposedly should not consume too much power because it is in equilibrium. But when no matter it's input change or the output load change, your error amplifier need to respond as quickly as possible, right? So we again use this another type of class AB input stage, and then with a 40K code, and then we can get into the error amplifier topology. So besides that, for LDO, if you want to have a low dropout voltage, usually people will use the PMOS transistor. But PMOS transistor will have less mobility. So if you use the NMOS transistor, actually the mobility will be larger, the on resistance will be smaller. However, if you use the NMOS transistor, then you need to have a higher dropout voltage. But if you use the 14K approach, you can tune the charge, and then you can try to move it back. And then also you can use capacity sensing and also capacitor to store the charge as a reference voltage. So this LDO doesn't need to have a band gate reference. And then also the open loop gain will be much larger because there's no resistive divider. So actually, and you can also start by itself. You can see like the error amplifier power supply actually is directly from the LDO output. So supposedly, if you can't do this kind of design, you have to worry about whether my output voltage start up, and then my error amplifier will, before the output voltage start, what can I do with my error amplifier, right? So it will become like a chicken and egg problem. But if you use the 14K approach, actually there's not a problem at all. You don't have to have a very complicated starter circuit. So we can actually program the charge, and then we can have different output level, and then everything will start nicely. And actually, we don't have to design band gate reference, and then we measure the temperature coefficient. It's exactly the same as the PIP capacitor, that capacitor which stores the charge, because the charge is not moving, but the capacitor itself has some temperature coefficient. It is about 22 ppm per degree C, and supposedly it should be okay for most of the application. And then the last part is the reconfigurable cognitive computation matrix and the analog gated recurrent unit. So this is some work we are doing in the last 5 years, because in Taiwan previously graduate students just want to work in the IC design company, so they want to work on conventional analog circuit, right? That's the reason why I make ADC amplifier filter, so that they can feel like I'm the traditional analog designer. But then after like recently, like AI become very hot. And suddenly people say, I want to do AI. I say, oh, okay, AI is good. So then we say, oh, can we do analog AI? So we try to say like, hey, can we, if you want to do AI chip, the first thing is you need to decide what is the memory you are going to use to store the weight, right? So in the first beginning, we think like SRAM should be the memory which can get access to all the process. So say, hey, let's start from SRAM. If we use the SRAM to be the weight storage, then if we can have an analog in and then analog out or digital out, and then if we can also take the digital in, then supposedly it will be a very nice cognitive computing matrix then, right? And then, so the challenge is like, if we want to bypass ADC, because we just mentioned ADC actually give you the ADC wall, right? The Nyquist array sampling, lots of data, lots of digital data, and you need lots of memory to store it, and you need to have a lot of data movement and consume lots of power. So the goal is to perform the cognitive computation without ADC. So we need to do the computation with analog sensor and input directly, and then we also want to support diverse kind of cognitive computation. So we need to have a programmable weight stored in the SRAM. And then we want to support different data formats because the weight can be positive or negative. And then the input data can be digital and can be analog. And then we also want this array can be tileable so that you can implement it as a multi-layer neural network. And then because the data movement is a power problem, we want to reduce the power, so we say computing memory, and then analog computation with process variation, so we need to try to have some collaboration strategy, and then we need to do some software co-design. So we start from this 1998 very classical later W2W later-based DAC, because this kind of circuit topology has very nice module, right? Like each bit, the transistor number of transistors are not too many, and then also they can use identical size of the transistor, and then so we say, hey, can we just slice it so that each of the bits can be one module, and then we can easily make this binary weighted current. So, and then the nice thing of this later structure is the input current is from I bias. So this I bias can multiply the digital weight naturally, right? You don't have to worry about linearity problem at all. So this is a bitwise topology, can be modularized, and you can duplicate this square, the LSB current. And then if you have a duplicated LSB, then you can do tooth complement. When you can do tooth complement, that means that you can do negative or subtraction operation without doing differential type of topology. So we try to make two of these later-based kind of DAC cascade, and then by doing so, the first layer we can have some constant current or I-in current, and the input digital bits can be stored in the dB. And then the second layer can store the weight, and then you can nicely to perform the multiplication of the current, the D bit and the word bit or weight bit. So you can support analog current, you can support digital input, and you can use the digital weight to easily modulate the weight. And then we try to merge these later-based transistors with extra 8 transistor with the 6 transistor SRAM. And then the colored, like the red one, the blue one, are the extra transistor in this pixel cell. And we can do the layout like this. And then, so we can have like one row will have 4 different pixels, and then they can array nicely. And then we can make words, right? And then we can have an array. And then we can have a digital SRAM to make the input array and then the bias array, because now we have the IDEC, we have SRAM, so supposedly we can modulate the current easily. And then we also design the nonlinear activation function as like Professor Random just mentioned, like digital activation function is very difficult for digital signal processor. If you can do it before ADC or during inside ADC, they can save a lot of power. So we try to use the current mode, and then once we have the current mode output, then we can actually use the current cascade, like current in, current out, right? And then to have implement multiple layer of the neural network. So this is the measurement result. We can program the chip to change some simple switches to make the connection, and then we can perform one quadrant or two quadrant or four quadrant kind of multiplication, so that we can support sine, unsigned times unsigned, unsigned times sine, sine times sine, like this kind of operation. And another interesting is like we can input sinusoidal wave in 4 different channels. The reason for 4 is just because we have only 4 DAC in my lab. So then we can do real-time weighted summation to do cosine transform. And this implies like we can do analog real-time vector matrix multiplication with nonlinear activation function in time-varying signal. Everything will be in analog domain. Only the weight will be in digital. And this digital weight can be positive or can be negative. So we have this kind of capability to support analog cognitive computation then. And then this is the activation function. So we actually can tune one of the common mode current, and then we can tune the slope. So by doing so, actually, this is kind of doing the normalization in analog domain. You know, like normalization is also very expensive in digital processing. But somehow, if you can tune the slope, then you can easily use the low power to do normalization. And then we try to make the chip cascaded. So we use 4 different chips and use the MNIST database. And because the MNIST has too many bits, so we try to do the maximum average pooling actually. So we get rid of the margin pixels and then get 8 by 8. And then we use 4 different chips, and each chip take 16 different pixels, and then we try to do neural network. So we try to use the chip, just chip to, and then use the board to make the connection, and then try to prove this feasibility. So we use 9 different chips to implement 3 layers of network to do MNIST. And because this is not a fully connected network, so and there is some mismatch, so the accuracy is not very good. But at least we can. This is our first trial, so this is kind of the setup. And besides our CCM, which is kind of like without any time or temporal information, we also have analog gated recurrent units. And the idea is like most of the biomechanical signals are time varying, so we really want to do some temporal classifier. And then we also hope like our analog classifier can be compatible with the digital one, so that we can use the PyTorch. We don't have to reinvent the tool chain by ourselves. And then by doing so, then we can do real-time recurrent cognitive computation without digitization, without digital memory for data storage. So this work actually is collaborated with Professor Kofi Odame at Dartmouth. So he visited me before COVID-19 in 2018. So actually he has a paper in 2022. So the idea is just like you can use the RC filter to modulate this forget gate and update gate. So it's just the low-pass filter. So depending on how do you make the low-pass filter, they will be equivalent. And by doing so, you don't have to digitize or quantize the time anymore. You can do continuous time kind of processing in RNN. So we make a chip, and then we have an LNA beside it, and then we try to have donor simplified output and then tied to an anti-bump circuit to mimic the energy extraction function. And then, so all the current will be positive then, become energy. And then we have, we actually take a neuron spike signal from NTU neuroscientist, Professor Lai's lab. And then we try to use the PyTorch and then compare with the cadence and then compare with the chip measurement. And you can see like from cadence to PyTorch, the correlation can up to 97%. And then for measurement to cadence is like 96. And for measurement to PyTorch is 94. So that means like we can pretty use the PyTorch to predict what will happen if I use this different analog GRU. And then so we can train like whatever people are using in RNN or GRU. So this is kind of the architecture. And then this is the spike sorting demonstration. So we have the database from NTU, and then we try to make the normalization and then signal square by using the anti-bump circuit. And then with this kind of positive current, then you have this kind of type 1 and type 2 neuron spikes. And then we try to use these two kind of current fit into our chip. And then we can observe the output ping to say like this is spike 1 or spike 2 to distinguish the category of the neurons. And then they tried like 2,000 different waveforms, and then accuracy can be 98.5%. And still it is a very simple case because they report to me like if there are two different like double peak waveform with very slightly difference, they still cannot distinguish it. And there's still some like precise capacitance. We need to extract the time constant and need to retrain it or to modulate. So correlation actually is a big problem. So I think online learning will be something, if possible, we should shoot for so that we can kind of calibrate the mismatches and variation. And this is in 0.18 microprocess. So again, like this is the era of the intelligent robotics and also the booming of the large language model, right? So now the issue is like, how do you connect so many number of sensors to the large language model, right? So previously people used analog to digital and then digital to token. And then because you digitize it using ADC, then you have lots of digital data, and then you have this digital data flood. And then digital data will always become the bottleneck, and it's the limit of the power efficiency. So because we have the analog GRU, so you can imagine this analog GRU can take time varying analog signal and then you can train it, right? So the output can be whatever kind of vector you want. So as long as you know what kind of token you want to train it, and then you can train it on the PyTorch and then get the weight and then install the weight in the GRU. And then supposedly the analog signal come, then the output pings will appear as what you train for. So that will become the real-time analog to token converter. And then we also have RCCM, which was mentioned. You can support different kind of input format. You can support digital input format and also the analog input format. So if you take the digital input format and then the output is current, and then because we can use that kind of cascade structure to make the neural network as a regression. And then depending on what kind of actuator you want to drive, you can always train this RCCM way to drive whatever driver you want to use. So I think we try to use these two circuit, analog signal processing circuit, to be the tokenizer or detokenizer. So conclusion. So I think the fusion of distributed analog flash memories actually break the rigidity wall, which means like previously when people design analog circuit, they only have one specific functionality for one specific scenario. But with the analog flash memory, you can program it so the same filter hardware. You can program it to generate different type of filter frequency profile. And then by using analog flash memory, actually you can take advantage of the capacitive circuit. Capacitive circuit doesn't have the DC current, doesn't generate noise, and then you can perform weighted summation without power. And then by doing so, actually we demonstrate this kind of approach can design very high performance and low power, low noise amplifier, LDO, and filters. And the nonlinearity enable autonomous circuit adaptation to input signals, and then can achieve high performance and low quiescent power. So this is very interesting because we always talk about event-based camera or event sensing, right? So if you imagine like even before the spike, there's some analog feature extraction circuit. If this kind of feature extraction circuit can also be event-driven, which means like the power only consumed when there's an interesting event, and then if there's no event, then your analog circuit will always at a very low quiescent power mode. Then they will kind of break this performance and low quiescent power bottleneck. So we demonstrate that in the ACABA, the autonomous current adaptation buffer amplifier, ADC driver. And also the fusion of computing and the memories break the power wall and the memory wall due to the reduction of the digital data bandwidth. So we use the RCCM and the analog GRU to demonstrate like intelligent signal processing doesn't need to use ADC. You can just use analog signal processing technique. And if you can take advantage of the nonlinearity of the memory and also the transistors, then actually hopefully it will be more closer to neuromorphic engineering devices. So thanks for your listening. And then I really appreciate this opportunity to share my design experience with you. And if you can give me any instruction or feedback, I'll be very happy to take. And then next year, I remember like Professor Yaki, actually, after the workshop, he came to Taiwan to visit me. So if any of you have the chance to come to Taiwan, you are also welcome to contact me. I'll be happy to host you. Thanks.